In the previous video, we saw the transpose of a matrix, and we used it to define symmetric and skew symmetric matrices. Let us now today note that if the characteristic of the field F is 2, then there is no distinction between symmetric and skew symmetric matrices. And what is the reason for that? Well, the reason is simple. Say a matrix is symmetric. This means that its transpose is equal to itself. However, we know that in a field of characteristic 2, 1 is equal to -1. And that translates, entry wise in the matrix this will happen, and that will translate into this. So a symmetric matrix is also skew symmetric. Similarly, if a matrix B is skew symmetric, then its transpose is -b by definition, but that is equal to b. So it is symmetric as well. And because of this, in the remainder of this section, we are going to assume that our field does not have characteristic 2. So we assume in the rest of this section that F is not of characteristic 2. All right. Now let us see how we can create symmetric and skew symmetric matrices. Instead of blindly looking for examples of symmetric and skew symmetric matrices, is there a systematic way of producing them? Yes, there is. Let A be any element in Fn. We are now going to express A as a sum of two matrices. One of them will be a symmetric matrix and the other one will be a skew symmetric matrix. Then you can check that, it's a simple thing. A equals this sum. Where we have used the transpose of A to write A like this. Note carefully that this 1 divided by 2 has to be interpreted in the underlying field. These are not necessarily real numbers, which means that this is the multiplicative inverse of 2 in the field F, which exists because 2 does not have characteristic, F does not have characteristic 2. So 2 is not equal to 0. That is why. And in fact, this is why we need it. Now, what is so special about these two matrices? Let's take the transpose of this matrix and see what we get. The transpose of this entire matrix. First of all, we can take the scalar outside. Why? Because it is one of the properties that transpose has. Okay, so we then get the transpose of this. And then you can take transpose inside a sum, that is also one property. Okay, so you get A transpose plus A transpose transpose. And finally, you also know that the transpose of a matrix is the matrix itself. So you are actually getting the original matrix back. So what does that tell you? It tells you that the original matrix itself is symmetric. Similarly, let us take the transpose of the other matrix also and let's see what we get. Again, the scalar comes out first. Now, to be a little more detailed than usual, let us first write this as A plus minus 1 times A prime. Just give me a moment, okay? Alright, so that we can understand precisely what is going on when we take the transpose inside, which we can do just like there. Now, we are first of all, ideally we have to take the transpose of this entire product. And then this minus 1 is a scalar, so it can come out. And we have transpose, oh I think I messed up, yeah, this will be transpose, this. And now only you can use this, what you did here, you get A back. So you can see that if you take minus outside, then you get this. Now I am not again writing minus 1 times A prime. I mean, we did that primarily to see how the transpose, what the transpose does when it goes inside. So we now have this. So this is not the matrix we started with, but it's negative. So this is skew symmetric and this is symmetric. This is symmetric and this one is skew symmetric. So we have been able to express any matrix in the matrix algebra as a sum of a symmetric matrix and a skew symmetric matrix. In particular, if you are given a matrix A, you can consider this matrix. It will be a symmetric matrix. You actually don't even need to divide by 2 to have a symmetric matrix, but if you want to express A as a sum in this way, then you need 1 divided by 2, or rather the multiplicative inverse of 2. Now, next comes the question, is this expression unique? Yes, it is also unique. If you write A as a sum of a symmetric and a skew symmetric matrix, then it has to be only this. There is no other way. Let us see why. Suppose I consider two possibly different such representations. Suppose there exist matrices A1, B1, A2, B2, in Fn such that A1 and A2 are symmetric, B1 and B2 are skew symmetric, and A1 plus B1 is A and A2 plus B2 is also A. Alright, then what happens? Let's see. Then what we can do, we can take transpose on both sides. That way we will get this. Now our focus is on these matrices, so we kind of leave A. Or, so you can take transpose inside the sums, A1 transpose plus B1 transpose equal to A2 transpose plus B2 transpose, or you can write more because you know that these matrices, some of them are symmetric and some are skew symmetric. So which ones are symmetric? A1 and A2, and B1 and B2 are skew symmetric. So this is what you will get. So you are having this equation, you just leave the middle term and you have this equation. Now if we add these two equations, what do we get? We get 2A1, which is A1 plus B1 plus A1 minus B1 is equal to A2 plus B2 from that equation plus A2 minus B2 from this equation, and this is 2A2. Okay, now we can multiply both sides by the multiplicative inverse of 2, which again exists because f does not have characteristic 2, and that way we get the fact that A1 has to be equal to A2. So A1 is equal to A2 and this sum is equal to this sum, so B1 should be equal to B2. And this is why once you express a matrix as a sum of a symmetric and a skew symmetric matrix, no other different expression like that exists. So what we found before this discussion, that one, that is the only one. Besides these sums, you can also, if you just want to have symmetric matrices, there are other ways also. Also, for any matrix A in Fn, both A prime, A transpose and A transpose A are symmetric. It is very easy to verify how. Let me just do it verbally. You take the transpose of this, so the transpose distributes itself over the sum, but the order changes. You remember that third property of transpose. So the transpose of this will be A transpose transpose times A transpose, but A transpose transpose is A, so you get back A transpose. That is why it is symmetric. Similarly, this one is also symmetric. All right. So after defining transpose and after learning about those three properties, we have an idea of generalizing this notion of transpose to something else more general, and this is something new. So looking at this generalization, you can see that this is how we always do mathematics. We find something interesting and then we take away its core properties, which themselves are interesting in some sense, and we create a new notion. And then the original thing from which it came becomes a special case. And this is how you, for example, define metric spaces from the distance functions you have in, say, between Euclidean spaces. Then from that you generalize to topological spaces. Okay, so things like that. Or you generalize from the notion of dot product, you generalize and get the notion of inner product in a general vector space. So this is the generalization. We call a mapping star from the matrix algebra Fn to itself and adjoint on Fn if for all elements A and B in Fn the following are true. Following are true means these following things are satisfied. A star is equal to A. Oh, and one more thing. Here we are saying that this is a function. So ideally, the image of, say, this matrix A under this function should be written like this. Or if we follow Herstein's notation, it should be written like this, A star. Because in many places Herstein writes the function to the right. However, there is another less common notation, which is this. In this case, because we know the source of this generalization, and there we wrote the transpose like this. In fact, some people use this notation in general for functions. It may seem very strange, but let me just show you how it looks. Say you have a function f from some set A to B, just a function. Then for any element x in A, under that notation, the image of x under f is written like this, x to the power f. Some people use this also. This is very uncommon, but it's still there. So in that sense, this notation has been used. A star means the image of A under the function star, so it will be another matrix. Okay, so we require this property, and then number 2, you recall the properties that transpose itself has. From there it's coming. A star plus B star. And finally, B star A star. There is another property that transpose has, which is that the scalar comes out. That, however, hasn't been included in this definition, because in this general definition, which will cover other such functions like our transpose, which are interesting but they do not have that property, that scalar multiple property, that they do not possess. Okay, so we do not make that property a part of this definition. We don't require this. Now we are going to see, just like our transpose, another such function, but in a special algebra, matrix algebra, where the underlying field is the field of complex numbers. Complex numbers, of course, they form a field which has characteristic 0, so no question of being of characteristic 2. For a matrix A whose ith row jth column element is alpha ij, and it's a matrix with complex entries, n by n matrix. We define A star, so this is our special star on this algebra, to be a matrix whose ith row jth column entry is gamma ij, where gamma ij is alpha ji bar, and this bar denotes complex conjugate. Okay, so it makes sense because these are complex numbers, this alpha ij, so we can consider their complex conjugate. And we switch the indices also, just like what we do in ordinary transpose. If the field is general, however, say F is a finite field, not of characteristic 2, but it still can be a finite field. There, however, this will not make any sense because those are something other than complex numbers. Now, the fact that this function, this really is a function of that type, right? Because on a matrix of this type, if we apply this star, then we are again getting an n by n complex matrix. You still have to see that these properties are true for this particular function, which is straightforward, and I am leaving that to you. If it is there in the exercises at the end of this section, then we will do it. Otherwise, I am leaving the verification that this is an adjoint on you, and it has a name. This star is called the Hermitian adjoint. Is it called adjoint though? Yes, Hermitian adjoint on Cn. Okay. Now, see, after defining our original transpose, we used it to define then symmetric and skew symmetric matrices. The same thing we can do for a general adjoint function as well. if star is any adjoint and A is in Fn, we call A symmetric under star if A star equals A. Okay, it makes sense, exactly similar. And skew symmetric under star if A star is minus A. And so we have defined it generally, that means this also works here in case of Hermitian adjoint. If star is the Hermitian adjoint on Cn, then a matrix A in Cn is called Hermitian if it's symmetric under that Hermitian adjoint. And skew Hermitian if it is skew symmetric under star. Okay, so Hermitian and skew Hermitian matrices, we have got to these concepts. Now there are some remarks that the author next makes about this Hermitian adjoint. Let me just put some ink first, and then we are going to see these three remarks. There are in fact some other things as well that one can consider about, which have been considered here about Hermitian adjoint, which we will however do in another video, and then this section will end. The first remark is this: so now star means Hermitian adjoint. Okay, with that understanding, if A is a non-zero matrix is in Cn, then trace of A star is greater than 0. Note that in general the entries of A are complex numbers. So there is no reason for the entries of say A star to be real. However, even then the trace of this is not only a real number but a positive real number, provided A is non-zero. Let's see how. It's in fact an exercise at the end of this section, but let us see now itself. Let A have this general entry alpha ij. Then we know what A star is. A star is gamma ij, where gamma ij is alpha ji bar. Hence, what can we say about A star? Now that we know the general entries of both A and A star, we can calculate the general entry of their product in that order, A star. So let me call it beta ij. You can call it anything. Where what is beta ij? Beta ij is summation alpha ik gamma kj according to the definition of product. Alpha ik gamma kj as k varies from 1 to n. Now let us write what these gammas are. Alpha ik, so gamma kj is alpha jk bar. The indices get interchanged and we have complex conjugate as well. Okay, so this is what the entry is. You cannot write anything else now itself. Okay, this far you can go with the product. But we want to know the trace of this. And what is trace? Trace is the sum of diagonal entries, leading diagonal entries. Hence, trace of, I think it will be better if I change the format. Let me write here. Trace of A star is by definition the sum of the diagonal entries of A star. That means beta I, where I goes from 1 to n. Now let's write what beta I is. So this is the outer sum and there is this inner sum. Beta I itself is a sum. So it will be alpha ik. In place of j, we now have to write I. So alpha ik bar 1 to n. Now you can see that you can write something here, something else here. So this is a complex number multiplied by its complex conjugate. That's the square of its absolute value. Now, to all these, you bring back the extra hypothesis that A is not equal to 0. A is not the zero matrix, which means that at least one entry of A is non-zero. What do you see here? What is this? This is actually the sum of the squares of the absolute values of all the entries of A, matrix A, because I and K are varying over all possible values independent of each other. And in this sum, at least one number is a positive number. The rest are non-negative because mod square. And that is why this is not just a real number, but it's a positive real number. So that's how, if A is non-zero, then trace of A star has to be a positive real number. What will happen if A is 0? Well, if A is 0, then A star is also 0. In that case, A star is also 0, so trace is also 0. So these are the two possibilities. Either the trace is 0 or it's positive, and it is 0 precisely when A is equal to 0. Did you see that in some sense this quantity is behaving like the norm of a vector in a vector space, in a non-linear space? The norm of a non-zero vector is always a positive real number, and the norm of the zero vector only is equal to 0. It is something like that. Now, from this first remark, we have a second remark. Suppose a number of matrices are being considered. Oh, we cannot take this as n. Let me take m, because n is the size of the matrices. The number of matrices we are considering has nothing to do with the size, such that A1 star plus A2 star, and like that, An star is equal to the zero matrix. Then we are going to claim that all the matrices have to be equal to 0. How? Let us take conjugate, trace on both sides. If we do so, and we recall that trace distributes itself over a sum, because this is one property of trace, we get this. Plus trace of am star equal to trace of 0, which is 0. The field element, in this case the complex number 0. So just now we have seen that trace is trace of this type of product is a non-negative real number, and it becomes 0 precisely when the matrix inside itself is 0. This implies non-negativity of all these terms in the sum implies that each one has to be equal to 0. A1 star and so on, Am star, all of these have to be equal to 0. But then again, by what we saw in the first remark, each matrix has to be equal to the 0 matrix. Okay, so we can say this. And there is a third remark also. The third remark is this: for any complex number lambda, lambda star is equal to lambda bar. This equation may at first look nonsensical, because lambda is a scalar. How are we taking the Hermitian adjoint of a scalar. We can only take the Hermitian adjoint of a matrix. Let's see what that means. You see, do not forget that whenever we write a scalar, when we are talking about operators and matrices, and you see a single scalar, and that scalar is being added and subtracted from matrices, from operators, you have to understand that it's just a shorthand way of writing. It's a shorthand for lambda 1, where 1 is what? 1 is the n by n identity matrix. So this actually is a matrix. It is this matrix. Instead of every time writing lambda 1, we just simply write lambda. In that sense, this is the Hermitian adjoint of lambda 1. And the right hand side similarly is that matrix which is lambda bar times the n by n identity matrix. Is it true? Let's see. We have lambda equal to lambda 1 equal to alpha ij, where if we write the entries, then it will become clear. Alpha I is equal to lambda for all possible I, and alpha ij is equal to 0 whenever I and j are different indices. Okay, so with that, what shall we get if we calculate the Hermitian adjoint of lambda? So this is equal to gamma ij, where gamma ij is alpha ji bar. So what shall we get as the off diagonal elements of this lambda star? Those gamma ij's where I and j are different, but for them alpha ij is equal to 0. So alpha ji is also equal to 0. So we are getting 0. Thus gamma ij is 0 for I not equal to j. And what about gamma ii? Gamma ii is alpha ii bar, that means lambda bar. So you see that in this matrix also, just like the original matrix lambda, the entries along the main diagonal are all equal to lambda bar, scalar lambda bar, and the off diagonal entries are all 0. So this lambda is a scalar matrix whose diagonal entries are lambda, and this lambda bar is the scalar matrix whose diagonal entries are lambda bar. That is why that equation is true. Hence lambda 1 star is equal to lambda bar 1, or more compactly this. So in case of the Hermitian adjoint, if we want to take a scalar outside, it doesn't simply come out as it is, it comes out with a conjugate. Although we haven't shown that here, but that will be a consequence of this. I leave it to you to see why. And with this, let's end today's video. Tomorrow we have analysis as usual, and we are nearing the end of analysis 1 of Terence term. 2 more results, exercises are there also, of course, but the theory part is nearing the end. And I am thinking of something else also that I will write in the community section, okay, about topology. But anyway, so see you tomorrow with analysis. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.